Okay, now I would like to demonstrate a little bit what's going on with the least square solution. About solution in the case when k is larger than n. Okay. So I would like to pick and A and M for us. Pick a measurement matrix, and actually, for simplicity, I'm saying let's pick a matrix where that already looks like our singular value decomposition. So we just have, let's say, 1 and 0 in the first row. Second row, let's put 0 and 1, and then in the bottom, let's have 0, 0. Just to start with something simplest possible case. So this is already like our D in the singular value decomposition, and U and V are just identity matrices in this case. And then we need a measurement vector, M. Okay, now a test. Are you awake? How many elements should M have? A stunned silence. Sorry for that. Anyone? Yes? 3. Yes, I think so too. But yeah. Let's start with just the 0 vector, again, keeping everything as simple as ever possible. In general, in computational science work, I highly recommend starting always with the simplest imaginable case, or maybe something even simpler. Make it work, and then step by step, with smallest possible steps, make it a little bit complicated step by step. That's, in my experience, is the only way to, the fastest way to produce bug-free code for any modeling. Okay, so we have this situation. Then I would like to plot for you the function of f. F is the vector in Rn, n being 2 in this case. So f is a vector in R2. So I would like to actually plot the function we are minimizing, this norm expression, on some subset of R2, so that we can see how it looks like. So let's create evaluation points for our function to be minimized. And let's take some maximal value. Let's take m to be 1. And let's say this is some kind of NF. Let's take 128. How many points we have in our discretization? Let's take clean space from minus maximum to plus maximum and NF points in between. And as you may recall from the last time, we will make F1 component and F2 component using the lovely mesh grid command. So now we should have a two-dimensional grid for the square going from -1 to 1, in both horizontal and vertical directions. We could take a look, like as another general principle is always to take a look of what's happening. And let's plot these points, F1, F2 as blue dots, and put axis equal so that it doesn't stretch in strange ways. And let's run this. Let's start with a little bit less points here to better see what's going on. here are the points we created. As you see, they span the square from -1 to 1, both horizontally and vertically. So it's a regular grid in the F space. Now next we want to compute the value of the norm expression, the norm of AF minus M at each point, and see how that function looks like. So let's evaluate A times F minus M. Well, on the blackboard I had M minus AF. Does it matter? Oh, okay. You are very much awake. Probably much more than me. Let's see how this goes. Evaluate this one at the grid points. Okay, well, let's call it, I don't know, big F. I don't know if it's a good one. Maybe not. Let's call it E for error in our system of equations. So this should be norm of a certain vector, and actually, well, we want something like A times F minus M. However, we don't have any thing called F here. So actually, I think we need to work with vectors. So let's drop our coordinate matrices to be vertical vectors, both of them. Then actually let's initialize this our function as zeros. Size, for example, f1, it doesn't matter if I take f1 or f2, they have the same size. And then let's make a for loop. 1 to length of f1. This certainly is not the most computationally effective way of doing this, but it's quick to code and clear to see what's going on. So now actually we have here A times f1 I vertical vector, and then f2 I. I think this should be okay. And it's always nice to monitor what's happening if we have lots of pixels and a long for loop to know how long it's taking. So let's, for example, say if let's say every 100 iterates, let's show where are we going in the run, just to know what's happening. And let's first see if this runs. It did. So we don't have so many points, but anyway, we saw these couple of displays here showing the progress of the run. And now maybe we don't do that anymore. Let's actually reshape everything. F1 is actually reshape F1 to the size. What did we use? We did use NF by NF. The same for F2 and the same for E. And now we can make a mesh plot. Mesh F1, F2, E. Let's see what happens with this. Okay, so here we see something like this, but it's maybe doesn't have so many points. We need more points to see more clearly how our function looks like. So actually, let's put here 256, for example. It doesn't have to be a power of 2, but okay. And actually, we want to get rid of the sharp point there at the bottom. So actually, it's much nicer to work with the square of the norm. So let's do that. That will be easier to analyze, and everything becomes nicer. And anyway, if we find a vector that minimizes the norm, the same vector will minimize the norm square as well. So let's take a look at this. Okay, and now we see what I really wanted to show you, that we are dealing with quadratic functions. So it's like a parabola for two variables. And it looks the same in higher dimensions. Well, I'm sorry for my visual teaching style. I really won't bother showing. Of course, this all could be proven using convex analysis and all that, but in this course, I mostly go by trying to convince you by pictures and small computations. All of this is really possible to go through rigorously mathematically, but we don't do all of that in the course. And now we can see what happens if in our A matrix the first singular value is rather bigger than the first one. What changes? We see that our function becomes a little bit elongated. So instead of circles, we have ellipses somehow as the curves of same value of this function. So the other direction is growing more rapidly than the other. But still, you see we have a unique minimum here. That's something I will not prove here, although for this simple case it shouldn't be too hard. Maybe it will be an exercise. But anyway, when we assume that all the singular values are strictly positive, what happens is that this guy has a unique minimum somewhere. The minimum, of course, may move if we, for example, change, let's put something like this. If we change our measurement vector, you see that then the location of the minimum will move, but the nature of this function will not change. It's still a quadratic function, like a parabolic bowl in 2 dimensions. And let me also show you, let's return to the simple one. Now, if we really have a 0 singular value, so only one positive and then the last singular value is 0, what happens then is we will have this kind of degenerate case. You see there is an infinite number of minima along a full line here. And that's what happens if we have, in a higher dimensional case, if we have several zeros in the sequence of singular values, there will be a higher dimensional subspace of minimum values. So even here there's an infinite number, a one-dimensional subspace here or a one-dimensional, well, line of minima. And we may have a plane or a higher dimensional Euclidean space of minima. That's why we define this minimum norm solution. Because then, you know, in this case, if we look for the minimum, it's not unique. We have a bunch of, actually an uncountably infinite number of minima. So how to choose? Well, when you study this concept of minimum norm solution, it means that among all the infinity of minima here, we will pick the vector which is the shortest. And that will be a unique definition of a minimum norm solution. But in today's computation, we don't have that. As you saw, I wrote the assumption that all of these are strictly positive, these singular values. So we will actually, in today's computations, we will have a unique minimum for our parabolic bowl in higher dimensions. How do you feel about this? Yes? Mm-hmm. Excellent question. I think we need some way of choosing. There has, I mean, because we have an infinite number of minima. Of course, we could say that, oh, take any of them. But in a practical situation, the end user wants to see an image or some result, some reconstruction, one somehow defined reconstruction. And taking the one that's shortest is just one way of doing it. Yeah. I think it has a special meaning because the square norm in physics is energy. So somehow it's also some kind of minimum energy solution. So it really is a special one. So from the mathematical point of view, or whatever, we just want to make it unique. But I think it carries more significance because of the minimal energy solution. So it can be seen as somehow natural. In some situations, it could be something that nature, like physics, would opt for, going for the energy minimum. There is a connection like that. But in some cases, depending on the application, we may want to take something else. So it's a, for example, when we deal with sparsity promoting inversion, in sparsity promoting inversion, we want something where most coordinates are zero and only a small number of coordinates are non-zero. In that case, we would take, among the infinite ones, we could take something that has many coordinates zero, and that would lead to a different choice. Yeah. Yes?
So, can you explain when we're dealing with pictures?
Yes.
Like the darkest picture, or what's then the minimum norm solution if we got a vector?
Ah.
So basically, I don't mean, you know, the darkest as keskiarvo,
mean average, yeah.
It kind of feels like, well, why choose that, but maybe it's not that.
It's, well, again, it is a good question why to choose the shortest one. One answer is just it's a very simple way of picking a unique choice that's always unique. And as you will see in your next exercise number 1, you see that it's also very easy to define using the singular value decomposition. This Moore-Penrose pseudo-inverse gives the minimum norm solution. So it's also very convenient from a theory point of view and from computational point of view. It just has many benefits, and also, yeah, well, I don't know. It's just a lot used, a very popular choice, and
yeah, in some cases, it's really, you know, you mentioned about the energy level, so it's kind of really important. But I just meant that if there's some other application that it's kind of meaningless, you know.
We will actually. It's very much related to the variational regularization. We will deal here with the Tikhonov regularization and total variation regularization, because there, in some sense, we are actually picking out another choice, another unique choice. That is actually something we are doing. Namely, this minimum norm solution, as you will see in the exercises, it will save us from Hadamard's two of Hadamard's 3 problems, namely non-uniqueness and non-existence, that may cause our problem to be ill-posed. Using this D plus operator, namely in the inverse of A, taking 1 over the singular value only for positive singular values and not doing it for zero singular values. That will give the minimum norm solution, but it will not save us from the instability from coming from the small final singular values. So in that sense, in ill-post inverse problems, the minimum norm solution is not a good choice. And therefore, we go to Tikhonov regularization and total variation regularization. So in that sense, actually, it is another choice, which is much more relevant for ill-post problems, unstable problems. So, well, maybe the answer is we will see other choices, and they will be very important. Okay, and still continuing with the idea of using pictures, I want to convince you about something. Let me use this video to do it. Let me play this video once. You see there is a point traveling in the plane along a line. And for each point, I'm drawing out as red the values of our norm function. And now my claim here is one that we will use in the computation we do next. That you see this line is traveling through the minimal point of our parabolic bowl. That's what the line is doing. The same can be done also in higher dimensional cases, although still the line remains the line, but it may be that our parabolic bowl is a function of more variables than 2. But a similar thing can be done in higher dimension. Now my claim is that now, even if this was in higher dimension, because our point is traveling along a line, this will draw out a parabola. Does it seem plausible to you? We have a quadratic form of several variables, but we are restricting on a line and following the value of the function. I claim this is a parabola, this red one here. Parabola of one real variable. And then the next point is, this parabola has its minimum point at the same point than the bowl. Right? Plausible. Proof by picture, proof by video. For many years when I was teaching this computation, in every course we go through the computation we do next after the break. And for years I had great difficulties in convincing the audience that about one step in the computation. Then I made this video, and after that, in my experience, it's much more clear what's going on. So we will, after the break in the computation, I will take a line going through the minimum point of our parabolic bowl. And I will claim that, so this is parametrized, this line is parametrized so that at the minimum point the parameter is 0. And let's say here it's positive and here it's negative. So it's like a real line placed there in the plane having the 0 point right at the minimum of the parabolic function we see there. And then my point is that the derivative of this second order polynomial, this parabola, the derivative is 0 at 0. How many of you think this is so? Okay, almost everybody. I know it's a little bit of, well.
You use your authority, like sometimes misleading us.
Of course, yes. That's what professors do. That's what professors do, but it is the responsibility of the students to learn independent scientific thinking. So I really encourage you to think for yourself and correct me when I'm wrong. That will happen often. And the whole point of university education is to help you think for yourself and learn powerful techniques for thinking that they are true. You can check yourself, so you don't have to trust any authority. You can think. That's the main point here. Okay, I think it's time for the break. So let's continue 15 past.